Hello and welcome to Module 4, Modeling and Simulation. Today we will talk about modeling simple systems. What we'll do Model 4.1, which is Electronic Assembly and Test System, 4.2, which is an Enhanced Electronic Assembly and Test System, and 4.3, Enhancing the Animation, 4.4, Adding the Entity Travel Times. We'll find and fix model errors and then do input analysis, such as specifying user input distributions for parameters, deterministic versus random input, collecting and using data, fitting input distributions via ARENA, input analyzer, what to do with no data, non-stationary arrival processes, and multivariate and correlated input data. So 4.1, Electronic Assembly and Test System, model looks below. You'll produce two different sealed electronic units, A and B. Arriving parts will be cast metal cases machined to accept electronic parts. So Part A and Part B will be in separate prep areas. Both go to a sealer for assembly and testing, and then to shipping output if okay, or else if they fail defects, they go to rework. From there, they will be reworked. They'll look at either salvaging and shipping them or scrapping them. Inter-arrivals will be at 5 minutes, and then from the arrival point, they would go immediately to the Part A prep area. In the process itself, it'll be a machining and deburring and cleaning, so it'll be 1, 4, and 8 minutes respectively. Then they go to the sealer, which requires assembling and test, or 1, 3, and 4 minutes. And then 91% will be a pass rate, or 0.91. And then from there, that 91% pass rate will go on. The 9% will go to the rework area. Of those rework area, there's a 45-minute processing, and 80% of those will pass. AKA 80% will go on independently for each part, and then from there, those that pass will go and be salvaged and essentially become a finished unit, or else the remainder will go to scrap. So for Part B, the inter-arrivals will be batches of 4 with 30-minute expo time. Upon arrival, batch breaks into 4 individual parts. They proceed immediately to Part B prep area, where they go to the machine deburring and cleaning process for 3, 5, and 10, and then go to the sealer for assembling and test with a Weibull distribution of 2.5 and 5.3 minutes, different from Part A going through the same station. They have a 91% pass rate, similar to the other one. All that pass go to shipping, the others go to rework, and those that go to rework have an 80% pass rate, and that probability independent for each part, and then go to the pass rate from there will go to salvage, and the remainder will go to be scrapped. Run conditions, so start empty and idle, so there will be, by empty, no units within the system, and it'll run for 32 hours. Collect statistics for each work area on resource utilization, the number in queue, and the time in queue. And for each exit point, shipping, salvage, and scrapped, we would like the total time in the system, which is essentially the cycle time. So developing the model approach. Now, those are our parameters inputs, so now we need to develop it. We need to define the pieces of the model, modules, data structure, and control logic at the appropriate level of detail. Sometimes that appropriate level of detail is a judgment call. In this case here is a simplistic model, so the detail is essentially given to us. Otherwise, this particular model, the entities are 2 different parts, so we have to have 2 different types for those. We have to have separate create modules for each of the 2 parts, and separate process modules for each prep area. The process modules for sealer and rework will each be followed by a decide module, which is a 2-way, either passes or fails by chance. The department modules will have shipped, salvaged, and scrapped, and the attribute sealer time is assigned after creates an assigned module. So the parts have different times at the sealer, and that's important to note. Record the modules just before the departs in time for system. So start with a new model, and then attach a basic process panel if necessary. So create the modules, place the modules, create, assign, process, decide, record, and dispose. So build those out, and then right-click on the last action to place the module. And you can auto-connect using either the connect button or using the pull-down menu. So the Part A create module, name it Part A arrive with an entity type of Part A. Type between arrivals will be random or exponential distribution with the pull-down list for 5 minutes. And then default everything else that's not included here. Part B will be a Part B arrive and a Part B entity type. Time between arrivals will also be random exponential distribution, value of 30 minutes instead of the 5 from Part A. In that case, we will have 4 entities per arrival. The Part A attributes assign module. We need to name it the assigned Part A sealer and arrive time. So we'll do an add button, type of attribute, sealer time, and use the new value for the different types for the triangular distribution. The add button, again, for attribute, arrive time, the time now, which computes the time in the system or on exit. Part B arrive time module will assign Part B sealer and arrive time. We'll have the attribute name and new value is listed below, and also the attribute name and new value for the time now as well. A couple good key points to remember when creating these in Arena. First of all, default names are usually suggested. You're welcome to include those, but I strongly encourage you to either leave them as they are or leave them with something else that's very descriptive. The name is placed in the appropriate pull down for future reference, so once you name it, you'll have it in there for future. And then all names on a model must be unique, even across different kinds of objects. If you were to otherwise create it and they were not unique, you could have the potential to overlap or change an element of your model that you didn't want to change. So in the process module, again, for Prep A process, and then we'll call the action the seize, delay, and release. The resources subdialog will have a resource pull-down menu, and then resource we'll call Prep A and the quantity of 1. Delay type will be triangular distribution, and 1 minute, 4 minutes most likely, and then 8-minute maximum. Part B prep process, seize, delay, release also as well. All these pieces are the same, except the distribution is a little bit different. 3 minutes for minimum, 5 is most likely, and then 10 for max. Again, it still uses a triangular distribution. The sealer process module will be a seize, delay, and release as well, and that has a delay type as expression, units or minutes, and the expression will be the sealer time. The sealer inspection result decide module. The decide module provides branch points by condition or entity attributes and global variables, or by chance, multi-sided, possibly based on a essential coin flip. We'll name this the failed sealer inspection, and we'll call this a two-way by chance because there's two options that it could be. The percent true will be 0.9, and then different exit points for true and false results, and connect them appropriately downstream. The rework process module will be a rework process with an action of seize, delay, and release, and the type will also be a resource. We'll call it rework, and then a quantity of 1. It'll be an expression, delay type, units will be in minutes, and the expression will be exponential distribution of 45. All these, again, are based on the original parameters we discussed up front of the model. The rework inspection result decide module, we'll call it name failed rework inspection, two-way by chance, default, and then the 20% true. So again, we call it 20% true. You could call it 80% true. Again, either way, it doesn't particularly matter as long as you maintain your model and you label it appropriately. So in the record modules, Arena will collect and record many output statistics by default, some of which you may want and some of which you may not. We want time in the system, the average and maximum of the parts sorted by their exit point. So we want them max in system whether by shipped, by salvaged, and scrapped. This sorting Arena will not do by default. So it would automatically sort by entity type if you had the entities checked, which we don't have. So record module can be placed in the flowchart to collect and report various kinds of statistics from within model run as entities pass through it, but for tally type output performance measures. Ship parts record module. So let's call this the record shipped parts, and the type will be a time interval. The records elapsed up until now, the T now, from when an entity attribute was marked with a timestamp upstream. There are several other options for type you can explore for the help button. And again, I implore you to pause the lecture and click through the help button and try that. It'll help you understand the components of the software and what it can do. The attribute name we'll call arrive time, which was defined upstream, and then the tally name will be the recorded ship parts. So the tally name will be to keep track of that and give us that output statistic. The dispose modules, 3 separate exit points for the 3 separate part disposition, shipped, salvaged, and scrapped. We could have directed all 3 exit types to a single dispose model if we wanted to. The separate ones, that way we get the counts of each of them. And then the separate disposed models also allows for differentially checking boxes to record entity statistics. So let's do run setup for the run control. Without this, the model would run forever because you have to have something in there to say the model needs to terminate. Essentially, that's part of modeling. The Project Parameters tab, you fill in a project title and analyst name, and then defaults for statistics collection, but we cleared the checkbox for entities earlier. The Replication Parameters tab, let's do the replication length. We set for 32 hours, and the base time units will be minutes for the inputs without the time option. So the different Part A and B entity pictures, the entity data model, just single click on a project bar, the row for each entity type, so you have one for Part A and one for Part B, and then pull down initial picture, pull down menu, select different pictures for each entity type. Now in running the model, you can check the button if you'd like, which will help identify whether you have errors. This is a good practice to do before you run your model, just to make sure that you don't have any errors before you go and run and crash your simulation. You can click on the go button or the play button and that'll automatically pre-check if you'd like. You can change the animation speed, you can pause it, you can step through it, or you can fast forward depending on your preferences. So in viewing the results, you'll get counters during the animation for the modules. So you get create, dispose, and decide incrementally, and then the process, the number of entities currently in the model. So you can stop it at any point in time or can look at it at the very end. You'll be asked at the very end if you want to see reports. What you get will depend completely on what you put in the run, setup, and project parameters. If you complete that and you didn't like what you got and you want to change it, or you forgot to add something, you can always go back and change those options and then rerun the simulation. So navigate through the report with browsing arrows. The tree is at left. Average, min, max, 95% confidence interval, half widths, those are all included. So it's generally difficult or unreliable to draw conclusions from just one particular run, which we'll talk about in a little bit. So 4.2, let's go to the Enhanced Electronic Assembly and Test System. So now assume that you have shown this model to a production manager. And when you do that, you've engaged your subject matter expert and the production guy who's there who tells you, okay, there's some additional things that you forgot to consider. So first of all, he pointed out that this is only the first shift and there's a 2-day shift. There's a 2-shift operation. So on second shift, there are two operators at the rework station and working 16 hours. So he also pointed out that the sealer is not as reliable as it could be and that there has to include uptime and rework. So you create a factor of uptime for 2 hours, exponential distribution, and then the repair times will be 4 minutes. He also wants to buy racks to hold the rework queue. So he can get a rack that holds approximately 10 parts, but needs to know how many racks should he buy. So in this case here, he says we'll run it for 10 days on 16-hour day schedule. So now we need to update our model to include resource schedules, resource states, and then resource failures. So run conditions. Let's redefine a day to be 16 hours, and you can do that under Run, Setup, and Replication Parameters. And then change the replication length to 10 of these days, because we're going to 10 days instead of just the one. Schedules, we can vary the capacity of a resource over time in the resource data module. So for the rework resource, change type from fixed capacity to based on schedule, and then 2 new columns. We need a schedule name and a schedule rule. Type in the schedule name, rework schedule, and then select a schedule rule. Wait, capacity decrease waits until the entity releases the resource, and break will be full, but maybe starter and late. Ignore. Capacity goes down immediately for statistics collection, but work goes on until finished, so the break could be shorter or gone altogether. Or preempt. Processing is interrupted, resumed at the end of the break. So in the schedules, we need to define the schedule that the resource will follow in the scheduled data module. So the row should already be there since we defined the rework schedule. The format type is duration for the entries based upon elapsed time past simulation start time. The type is capacity for resource schedule. And then click on the durations column and get a graphical schedule editor. Make sure that the x-axis will be time and the y-axis will be resource capacity. And then click and drag it to define the graph. The options button can help control the axis scaling, time slots in editor, and whether the schedule loops or stays in a final level forever. And we can also use the graphical schedule editor only if the time durations are integers with no variables or expressions involved. So there's a bit of a limiting factor to consider. Alternately, let's right-click on the row and then select Edit and via dialog, and then enter the schedule name. We'll enter pairs for capacity and duration, as many pairs as needed, and then we can involve variables and expressions there. Another alternative, you can also right-click on the row and then select Edit for the spreadsheet and enter the capacity, value, duration pairs there. So resource failures. We need to add this in now, and usually this is handled for random or unplanned downtimes. We can start the definition in resource or failure module. So here we'll start in the failure. Attach the advanced process panel if needed. A single click on failure gets a spreadsheet view. To create a new failure, double-click and add new row. Name the failure, and then the type, time-based, count-based. In this case here, we'll do time. And then we'll specify whether it's uptime, downtime, and with units for both. So attach the failure to the correct resource. You'll need to use the resource module and failures column and sealer row. Click there, get the pop-up failures window, pick failure, name seal your failure from the pull-down list, and then choose the failure rule from wait, ignore, and preempt. We can have multiple failures acting on a resource if we so choose, as long as they are listed as separate names. And we can reuse defined failures from multiple resources if that's appropriate. Frequencies. Record time persistent occurrence frequency of a variable, expression, or resource state. So we'll use it here to record the percentage of the time of rework queue is of length. So since the racks hold up to 10, we want to know how many racks we need. So we can say 0 to 10, 10 to 20, 20 to 30, etc. and get an idea of saying how often would we have used this many racks if this is how many you were to purchase. The statistic data model under the advanced process panel, we have different statistics options, so frequencies is one of those. We'll want to specify the name, rework queue statistics, frequency type would be value, and then specify the expression to track and categorize. We'll right-click in the field to get the expression builder. We'll report the report label, rework queue stats, and then pop up the secondary spreadsheet for categories in browse file. Add another frequency in the statistic module to give a finer description of the sealer states. This will produce statistics on proportion of the time the sealer is in each of the 3 possible states of busy, idle, and failed. The frequencies will not be part of the default category overview report, so if you want to change that, you have to go and update that before you run your simulation. The results of Model 4.2 differ from those of 4.1 for a few different reasons. Of course, this one is a bit of a longer run, and we've also changed some of the assumptions. The prep for A and B didn't change. That's no particular surprise other than just some variations for the run length and random variability. And then the sealer is definitely more congested because it's got the chance for failure. Rework, incidentally, is less congested because you have it staffed higher. Frequencies report suggests 1 rack suffices for about 95% of the time, and 2 racks will be sufficient for all the time. So that might be a good answer to go back to the production manager and say 95% of the time you can account for it on 1 rack. Maybe cost or space are considerations. You can probably get away with just 1, but if you really need 2, that should cover everything that we've seen. This is a good example of changing some parameters that might come up in the modeling and then rerunning it and comparing it to your previous analysis. So just some finer points in there. 2 utilizations were reported for each resource. Instantaneous utilization is the time average of ratio of number of units that are busy to number of units that are scheduled. And scheduled utilization is the average number of busy divided by the average number available. Just 2 different ways of looking at that. Identical for fixed capacity resource, and that can differ for resources on a variable schedule. So if a resource capacity varies among several different positive values, it's better to use a scheduled utilization. If you want to see more issues and even more definition on finer points, see the textbook. There's more detail in there that I've chosen not to get into here just because we're at an overview status, but the textbook has a good level of detail to provide some of the things that you might run into when you get into modeling. So now Model 4.3, now it's time to enhance the automation. So let's get Spartan generic default animation for some things. So we can get some things for queue, connector animation, movement, that sort of thing. This is usually sufficient for verification and validation aspects. Often you want to customize it and enhance it a bit. It'll give you a little bit more realistic view. It looks more real towards your specific applications. And then you can pull animation away from the logic in the model window, particularly used for big models or complex animations. Default animation objects are connected to the model logic and move with the module. So identifiers and physical location you can change by shift and dragging to break those. You can also change animation cues. You can lengthen them by just clicking and dragging them. You can rotate them. You can change the form of the cue from a line to a point based on the type of entities you want. Again, all these may be applicable depending on your model. Changing your entity pictures. So earlier on, we used entity data module to assign a different initial picture to the entity types. You can certainly customize it under the Edit Entity Pictures option. And I won't go into those particular details in there, but if you'd like to pause the lecture here and play around with that, I certainly support and encourage you to do so. Adding resource pictures. You can animate a resource by using the resource button on the Animate toolbar. Or you can get the resource picture placement window. The left column is the default pictures for different resource states, and the right column is picture libraries. So adding variables and plots. Variable animation, just show a value of something as a number and then you can watch it change. So you can add the object from the Animate toolbar, and then you can double click and specify the expression to be shown in the expression builder. Dynamic animated objects is much more details available within Chapter 3, and then other animation objects you can use from the Animate toolbar. So now let's look at Model 4.4, Electronic Assembly and Test System with Part Transfers. So let's start with Model 4.3, and now let's say all part transfers take 2 minutes. So there's actual travel time. You want to have the model animate this, and you want to make some changes in there for the model logic and results. So the 2-minute transfer times will be applicable for the arriving parts to prep, departing to the appropriate exit, and then any other internal transfer from one station to another. Transfers will take 2 minutes regardless of distance. Obviously, this is not realistic. Later on in the textbook, while we won't get into that much detail here, it does give more color and clarity on how you would go and change that or have that adjusted for depending on where you're at in the model. So new constructs will need to have a station, which will be the location where some of the process occurs. So arrivals and manufacturing cells and departures will give each station a unique name, and this can serve as an entry point for a section of the model logic. And the station marker shown here will represent a logical station in the flowchart animation. Station transfer are entities moved between stations without the direct connection. So several different types. For these purposes here, we'll use routes, and we'll represent the routes with route paths in the animation. So adding the route logic from arrival. So stations and station transfers will affect both model logic and animation. So we'll start with model 4.3 and change it to 4.4. For incoming parts, A and B, we'll want to delete the connection from assigned modules to the prep process modules, and we'll replace them with the station and route module pairs. So the station module from the advanced transfer panel will define the entity's location, model name versus station name, and then the route module from the advanced transfer panel will send the entity out for the route name and with the route name and destination station. No direct connections exiting from the route modules. So the route module's destination station name will define that. Continuing with that logic, we'll add station modules for entry to each prep station. So the station names are Prep A and Prep B stations. Process modules for Prep A and Prep B will stay the same. After the prep, the entity is connected to the route module to send to the next station, which will be sealer. We don't need a separate station module for outgoing slide. Similar changes for the rest of the model. So station modules for incoming parts into the sealer, rework, etc. And then route modules for the outgoing parts of sealer inspection and rework inspection. We could run the model now and get results, But what we did also want to add with this model was the animation of transfers. So if we've done all this to this point in time, the model would go and run, but we're going to take a step further and walk through the animation process. So we could, the question might be, why would we just not add delays? You could just go, instead of going and adding a transfer time of 2 minutes, why don't we just add a delay up there? Simpler way to get a 2-minute transfer time. You could insert a process module with an action of delay for 2 minutes on each connection, or just use the delay model. So it would work for modeling numerical output viewpoints, but it would not show any of the animation. And for our purposes here, we want to be able to see the model run and flow, which is a vital element of the simulation. So altering the animation for stations, you'll add animations for the stations and routes using the station button and animate transfer toolbar. So attach the identifier to it from the pull-down list of station names. Get crosshairs, place and click a marker on the animation, and then can place several station markers for the same logical station. So you can represent incoming, outgoing sides, for example, and you can drag the station markers around later if you want. The routes, we'll use the route button from the animate transfer toolbar. The options for appearance of entities as they travel route, get the crosshairs, click on origin, destination, station markers, and then drag around endpoints. Don't worry about the corners for now. And then alternately, you could also use the route animation to create both station markers and route animation. So click for beginning a station marker, intermediate clicks for route markers, double click for ending a station marker, and then go back and double click on the 2 station markers to define their logical identifiers. Either way is acceptable. So the entity pictures, the Part B arrivals are in batches of 4, if we recall. So the constant travel time to Part B implies that they travel all together. So it'll look like just a single part, even though they're in a batch. So just if you'd like to try, you can go and change the route time from 2 to exponential of 2 to see the separation along the route. Otherwise, you leave them static, leave it as is, and it'll show it as 1. That you could create a dishonest illusion to animate the batch using the steps below. Assign the module just after Part B arrives. Add the assignment of entity picture to picture-dot-batch B. Edit entity pictures, draw a new picture. So you can copy picture B and rename it. And then when the batch arrives to Part B, change it to a single circle and add assign module after the Part B arrival. So creating your module, done. Assigning the animation, done. Now let's talk about finding and fixing errors. If the error prevents you from running, the Arena will try to detect it and will try to point you in the right direction. It'll pull you into anything such as if you have an undefined variable or attribute or resource, something that's not connected, it'll point that out. If you have a duplicate names, and the text will also give you all different sorts of errors. The text is a good thing to keep handy if you get into more simulation modeling, because you may run into that error and want to look it up, and that'll give you a good go-to resource. You highlight active module, selects the active module during the run animation, and then view layers while running. If you change what shows during the run animation, that's where you would do it. Module break, you can stop when the entity reaches the module, and then there's a debug bar under the View Debug Bar menu. So specifying the model parameters and distributions, the structural modeling is essentially what we've done so far. It's logical aspects, entities, resources, paths, etc. The quantitative modeling, numerical distribution specifications, it's a lot like structural modeling where you need to observe the system operation and take data if possible. Deterministic versus random inputs. So remember, deterministic is a non-random and fixed value. So the number of units in a resource, transfer time, inter-arrival time. Whereas random, or stochastic, as we've talked earlier, is a model as a distribution or draw or generate values to drive simulation. So transfer, inter-arrival, processing time, those things can be variable. So don't just assume randomness away. Make sure that it's valid and go and validate if there is variability to consider. So collecting data, age-old problem. Collecting data is hard, expensive, frustrating, and boring. The reality is it's a lot of labor in order to go and collect. And also, as tedious as it can be, it's also very critical to be on top of it, because a minor data collection error or interpretation or measurement issue can really wreak havoc on your analysis. So sensitivity of outputs to uncertainty in inputs. Again, better quality data coming in, the better quality of outputs you get. And then match the model detail to the quality of data. So you can look at this in cost, and you can capture the variability in data. Don't just assume something is static. Consider it being dynamic. Assume that variability will be present. And if you have a concern, or if you hear of a concern in the data collection components, make sure to go and validate that and prove or disprove it before finalizing your assumptions. So alternates and issues with using data. You can use data directly in simulation. You can read actual observed values to drive the model inputs. All values will be true, but you can never go outside of your observed data. So an analogy I've given in the past is if you say, hey, by the time I was 18, I'd grown 5 feet from when I was 1 year old. That means that in another 18 years, I'm going to be 10 feet tall. Well, that's obviously not the case. Your measurement system is only from 0 to 5 or 6 feet tall. It's the same here with the data. You cannot make assumptions necessarily outside of the bounds of what you collected. If you want to extrapolate further, you need to go and collect more data to validate that the model that is still a logical assumption. You can also fit probability distribution to the data. You can draw or generate observations from this distribution to model, to drive it. So you can go collect data and prove that there's a correlation. Then you can kind of create your assumptions in there and pick values in between. So ARENA has a pretty good tool called the ARENA Input Analyzer, where you can fit distributions to your data. So if you have your sample data, you can input it in there, and then it'll give you an expression that you can use. This will be very helpful because it also aligns with the other ways that you can express the data within ARENA and input it into your model based on the real-time data that you actually have. So in fitting the distribution, you have to decide on the distribution form. There's exponential, gamma, empirical. I mean, there's many others in there. I would suggest select different methods and utilize hypothesis testing, which I won't get into at this point in time here, but this is a good tool to validate whether or not your assumptions are okay. You could fit your theoretical to an empirical distribution, continuous versus discrete, best fit from others. It's a very versatile tool with a multitude of options. So the data files for Input ARENA Analyzer, you create the data file, however, whether it's an editor, most likely a spreadsheet, but it can also be in a database dump or some point. It can be you can open it in there, you can do new, or you can use an existing one, import it. And I would encourage you guys to even create some dummy data, create some random or pull something from a professional application in there just to try it around and see how it fits. So the fit menu that fits distributions and does the goodness of fit tests. You'll fit a specific distribution form, so plots density over the histogram for the visual test, gives actual expressions, and then also gives a goodness of fit test. So it'll tell you how well the model fits. Best way to judge this is to utilize a p-value. That's kind of a light discussion here on hypothesis testing, but if the p-value is less than 0.05, that means that the likelihood that fit is due to just random chance is less than 5%. And so at that point in time, if it's less than 5%, you can say that you're 95% confident that the distribution is a good fit. So you can fit all the ARENA's theoretical distributions within there. You can fit one or fit all. And so again, I'm not going to go through all these in here, but definitely take some time, pause the lecture, and play around with this a little bit. Issues with fitting input distributions. Remember, it's not an exact science. You're fitting, you're doing best fit, and again, you're only getting, you're comparing theoretical data, but you don't really know for sure. So you can say I'm 95% confident, but you can't ever say you're 100% confident. Or you may not get 95% confident, and you may be 75 or 80% confident, depending on your application. That may be okay. Consider the ease of parameter manipulation. Consider how much this may impact your model. Again, the advantage of simulation is you can run it a million different ways and try it each time. So if you're not sure about something, you could try it one way or try it a more conservative way, and that'll tell you whether it's a valid approach. So what do you do if you have no data? People never want to answer this question because everybody always wants to have data, and especially engineers, they don't want to make decisions without data. They want facts, logics, and information. But the reality is data is not always available, and oftentimes even when it is, it may have questions or it may just not be valid or believable. There aren't really a lot of good solutions. I mean, the most obvious solution is go get data. Sometimes that's not feasible, sometimes that's more feasible than others. The reality is there's a lot of bad solutions, but none of them are as good as going and get data. You could go and do interviews. You could go and talk to the production manager and say, how often does this machine go down? Well, I'm roughly guessing that it's running about 80% of the time. Depending on how critical that is, that may be acceptable. If not, that may not be, but it still may give you an idea where you have a starting point, and maybe you go and collect some data, and if it validates that assumption, that gives you a little bit more confidence in it. You can look at inter-arrival times and just evaluate that. The number of random events in an interval. You can use the Poisson distribution, for example, so you can go and spot check if it occurs here and occurs here and occurs here. That's where the Poisson would come into play. You could use a sum of independent pieces. You could use a product of independent pieces using different, again, you could leverage different distributions. Caution using normal distributions. People oftentimes have an obsession with data normality and try to make data normal even when it's not. So you got to be very careful with that. The other thing you got to realize too is in a true normal distribution, it could go on forever unless you have some sort of bound at the end, which oftentimes you do not. And the more data you get, theoretically, the more likely you are to have those tails on the far edge. So you also have to realize that if you have a point, for example, you cannot get a cycle time less than 0. You cannot have a percentage greater than 100. So you got to be careful about listing those bounds, otherwise simulation will give bad information. Also realize too, if the average is big relative to the standard deviation, again, the p, which is the negative value, is small. It could come down to very small and be very unlikely to happen. But the reality is, very small likelihood things can happen, and if you don't run your simulation long enough, you will not necessarily catch it. So non-stationary arrival processes, events such as arrivals, as we'll talk about in this instance here, the rate of those varies over time. So you think about when people arrive. For example, lunchtime at a fast food restaurant, it's going to be much busier at noon than it would be at 2 p.m. or 10 a.m. Rush hour, telephone call centers, things like that, those do change based on other conditions. They are not 100% random at all. It can be very important to model for this, because these also can, if you miss this, these will ignore peaks within your model and bottlenecks and give you a poor definition or poor information for following your simulation. So a good model would be to use the non-stationary Poisson process. So a couple of issues. First of all, you have to specify the rate function there if you're going to do that, and how to generate it from it properly during simulation are things you have to figure out. Several ways to estimate that rate function. That first one, you can do piecewise the constant, which is dividing the time frame of simulation into subintervals over time, which you think the rate is fairly flat. Compute the observed rate within each subinterval. And in ARENA, you would then have to convert the expected number of arrivals per hour into subintervals that need not to be of 1 hour length. So you want 45 arrivals in a half hour, you'd have to specify rate per hour. So you basically have to convert it back to an hourly basis. Example model 5.2 in chapter 5 discusses this further. Multivariate and correlated input data. Usually assume all generated random observation in a simulation are independent. That's usually a fair assumption, but not always the case. So a difficult part might require long processing in both the prep and sealer operation. It's possible that you might just get one bad part that goes through and just becomes difficult for all things bound. In this particular case, there's a correlation. So ignoring these things can give to an invalidated model, because if it's a bottleneck at the very beginning and creates a bottleneck behind it and then goes up further and is a bottleneck again, that's a different behavior than if those potential bottlenecking factors were random across all different parts. So won't get too detailed into here, other than to say that's something that in advanced modeling you need to watch for. And if you want to learn more about it, the text has more information about how to handle and even address some of those situations.